In the previous video, we talked about the vibrational frequency of a molecule and then the harmonic approximation of a diatomic molecule. In this video, we'll continue with our introduction with our molecular vibrations IR videos. Okay, harmonic oscillator is an ideal oscillator, and in real life, molecules really do have elastic limits, meaning that if you compress a molecule, the energy goes up, but if you expand the bond, if you keep applying energy enough, it will break the bond. So what this means is that the vibration of a molecule is not entirely harmonic. You say that it is anharmonic, so that's why we're talking about anharmonic approximation or anharmonicity. One of the potential energy that relates well with this is called the Morse potential. A sample graph is given here. The orange graph represents the harmonic potential, and then the red line represents the anharmonic potential. So it's given as V equals h Planck's constant speed of light, dE, that is how deep the well is from here to the maximum line, and d naught is the dissociation energy. So that's the amount of energy that you can put into the bond to actually separate the bond. Let's take a better look at the Morse potential. We have our energy levels no longer V plus half into HV, but we have an additional term there, V plus half minus XC into V plus half squared. If we want to work accurately, there's some smaller additional terms that are included anyway, so everything multiplied by h times frequency. Xe is called anharmonic constant, and it's a measure of the deviation of the vibration from harmonic approximation. It is small and positive. And there are some other terms that include other anharmonic constants that are also small, and as the series goes longer, the number is smaller. Now, the 0 point energy in this case is now, so if we put 0 here, we have half, and 0 here, that's plus half squared, so that's 1/4xe h. Our dissociation energy, which is the energy required to break the bond, that's the minimum energy required to break the bond, and then the depth of the well is now dE, because this is the 0 point energy right here, the minimum energy that the molecule can have, which is the distance, and d naught is the distance from the last vibrational energy level to E naught. So the energy levels are also not equally spaced again. So this, unlike in the harmonic vibration where everything is h. So if we put V plus 1 into that equation, minus V, we arrive at 1 minus 2Vxe HV, where V is our vibrational quantum number. Now, another consequence of this anharmonicity is that the number of vibrational levels is now finite. Because the bond eventually breaks with the appropriate amount of energy, then we have a finite vibrational level, unlike for the harmonic approximation where it is infinite and no energy level exists after the maximum. So the selection rule in this case allows V to change by values other than 1. So V can change values by plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. So these are our energy levels. The allowed transition, you can go from 0 to 1, 0 to 2, 0 to 3, 0 to 4. You can go from 1 to 2, from 1 to 3, from 1 to 4, and so on and so forth. The fundamental transition, that's from 0 to 1, is 1 minus 2xeV, and this equation is given in wave numbers. In joules, it will be 1 minus 2xv vibrational, so this is wave numbers, so vibrational h times h. The transition from 0 to 1 is called an overtone. So when you have V changing by plus 2, plus or minus 2 and above, we call them overtone. So the first overtone, that's from 0 to 2. So 0 to 1 is fundamental, 0 to 2 is now an overtone, and it's the first overtone. The second overtone is from 0 to 3. So the third overtone will be from 0 to 4. So a first overtone occurs at a transition 0 to 2, and then the second overtone 0 to 3. So we just put it in the energy equation. So that will be 3 plus half minus 0 plus half, and we arrive at 1 minus 3xe into 2v. What we notice, you know what, xe is a small number, so if xe is approximately equal to 0, then we have our harmonic approximation. If x is approximately equal to 0, we see that the first overtone will be 2 times the fundamental translation. So x is not large as such, so the first overtone usually occurs around that. So let's look at the differences between harmonic and anharmonic oscillation. The energy level in the harmonic approximation is V plus half HV. So we're back to joules now. In the anharmonic approximation, we have anharmonic constants multiplied by V plus half squared. And we have other series in the equation, which is often truncated at the second series. So the 0 point energy for the harmonic approximation is half h of the frequency. Here it's half minus 1 over 4x h frequency. The selection rule only allows for harmonic approximation plus or minus 1. Here the selection rules allows for overtones. So here we have fundamental and hot bands. Here we have fundamental overtones and hot bands. There's a constant spacing in the harmonic approximation between energy levels, subsequent energy levels. In the anharmonic, the spacing are not small. They keep reducing until a maximum energy level is reached. And at that point, the convergence is so much, and we call that the convergence limit. Here, the energy can go as high, infinitely, but in harmonic, the energy values cannot go to infinity. So, the energy levels, the maximum energy levels. Another thing about the vibrational frequency is that when you change from one isotope to another, the vibrational frequency, which depends on mass, changes. Vibrational frequency is inversely proportional to 1 over the square root of mass, which means that if you change to a lower mass, the vibrational frequency increases. If you change to a higher mass, the vibrational frequency reduces. As to recall that isotopes are atoms with the same number of electrons, but different mass number. So we'll continue